Welcome to your HDPE resources, the second webinar in a series of 4 provided by the Alliance for PE Pipe along with WL Plastics and Core and Main. Please note that this is a sponsored event and any opinions expressed are those of the presenters and do not necessarily reflect the views of ASCE. ASCE also asks that presenters and participants refrain from discussions surrounding competitors and pricings of products and services. And now it is my pleasure to welcome back for the 3rd year providing valuable HDPE sponsored webinars with ASCE, Alan Ambler. Welcome, Alan.
Thank you very much. Really appreciate being here, Robin. ASCE has been a great partner over the years, and we continue to be really passionate about telling great information out there to everybody out there. So before we get started here, we're definitely going to talk about the resources that are available to you from the Alliance for PE Pipe. So if you are starting your HDPE journey, or if you're farther along and you've gotten into a real technical detail, that you've got to be able to have a resource to make happen for you to be able to perform your analysis, then this is the absolute right webinar for you. One of the things that the Alliance does that makes these webinars so much more interactive is the fact that we encourage you to ask questions as we move through this. And then we have 3, sometimes more, 4 or 5 people behind the scenes ready and waiting to answer those questions. So even before this webinar started, we did get 2 questions through ASCE, and I could tell today is going to be a great day for that. So who is the Alliance? The Alliance for PE Pipe is a nonprofit organization focused on education for use of high-density polyethylene within the municipal water and wastewater market. So the people that make up the supporting members of the Alliance are all the companies that you see here on the list in front of you. So we'll have people that manufacture the pipe and fittings, people that distribute the pipe and fittings, contractors that install them, consultants, all sorts of different people involved in the overall municipal HDPE project through this. So a lot of different people providing great technical information to us to support you and your municipal project as you move forward as well. We're fairly active on social media, so whatever platform that it is that you prefer to utilize to be able to check to see the current events and ongoings of your friends and also the industry on whole, make sure you check us out at any of these social media platforms. Rather prolific in our posts to be able to share that HDPE story that we just love to talk about. Here's a list of some of our upcoming shows. So when I say that we love to talk about HDPE, this is the proof in the pudding. We've got lots of different shows for you, well beyond webinars. Our webinar program has proved very, very successful to be able to put us in direct contact with you that's asking those important questions and in the throes of actually doing the design and constructing those projects. But we also have road shows and general trade shows that we're a part of, and we try to endeavor to bring lots and parts and pieces of HDPE that are involved in these projects for you to touch and feel, and then also meet with the experts in your region that you can immediately discuss your project specifics with at that location. Another thing that we do is provide a whole lot of free resources. That's going to be part of the primary discussion today that we have with the industry resources for you, but you can schedule a seminar. We do perform detailed project reviews for plan reviews, spec reviews. We do look at spec editing if you need to be able to check with us to see how your spec is sitting, if there are improvements, or if you've noticed a deficiency in previous specs. You can open up that conversation with us and be able to talk to the experts learn from their mistakes. It's often way easier to learn from somebody else's mistakes, but that's kind of the best way we learn is from failure in that matter. Some more free resources for you, this engineering package. If you'd like to be able to get a copy of that engineering package, we do have a contact for you on this page as well. A lot of things within that package is searchable PDF for PPI's Handbook on Polyethylene Pipe, or the Alliance for PE Pipe's Insider's Guide to PE Vocabulary, AutoCAD format plus PDF format, typical details, specs, all sorts of things that are involved in these engineering package for you to be able to take a look at. On our website are a bunch of case studies as well that you can see previous projects that are performed informed within that area. Here's a list of contacts. This would be a good time to be able to screenshot those involved in our presentation today. Screenshot that photo so you can get access to them. We will show this numerous occasions throughout it as well. If you're looking for PDHs, there will be a survey at the end of the presentation, and enter in that information. That'll be the quickest way for you to be able to get those PDHs that you're after, as that's immediately queued for our process to be able to send that right out to you in the most expeditious manner possible as we go through. Here's a couple of acknowledgments. So it's not just the Alliance here talking to you. We have built upon years and years and decades worth of information, analysis of how HDPE works within the municipal water and wastewater markets. And then we're trying to bring that to you in this educational program as succinctly and clearly as we possibly can. So there's lots of different perceptions, chemical engineers, manufacturers, different mechanical engineers that look at all of this. And then we've tried to reframe all of that information, which is a lot of information from a civil and environmental engineering perspective for the municipal crowd, which is you. So thank you very much for attending these webinars as well. So now I'd like to bring on Rusty Reeves, who is part of our team here. Corin Main has helped sponsor this webinar so we can get in front of you and start to talk about all of the successful technical resources that you may have, and then also be able to help you with your projects as you go through. So Rusty, go ahead and tell us a little bit about you, and then Corin Main.
Yeah, thanks, Alan. And we love the opportunity to work with ASCE on this and really getting the word out about HDPE piping systems. I've been involved in the industry for over 30 years. Corin Main, we've got about over 300 branches coast to coast, as well as Hawaii and Alaska. We've got over 500 fusion machines. Really there just to support you, and love getting the word out. So appreciate it.
Now, Richard Glossa, thank you very much. Rusty is going to come back and join us throughout different case studies and then also other things throughout. So Richard, thank you for being here.
Hi, good morning. And my sentiments as well for ASCE allowing us to do this and educate you guys. I've done several of these, and I think some of you may be familiar with me and not, but I'm the technical manager for WL Plastics, one of the largest polyethylene pipe manufacturers in North America. So if you have pipe questions, please don't be afraid to ask. We've got lots of experience and lots of knowledge and lots of information to give you, so you don't have to really spend a lot of time to figure it out. We hope to give you your answers.
All right, Richard, thank you very much. We look forward to your input. Today, we're going to include Richard and Rusty, as you've seen, but also Stephen Burrows, who's the VP of Engineering at Pipeline Plastics. So it's not just one talking head or two. We've got lots of people up here to give you different perspectives. Stephen, you want to come on and tell us a little bit about yourself?
Sure, Alan, thank you. Yeah, my name is Stephen Boris. I'm Vice President of Engineering for Pipeline Plastics. Like Richard, we're a large polyethylene pipe manufacturer as well. And like many of the panelists here, have a wealth of experience, 30 plus years in polyethylene pipe and all avenues of it. So very happy to come on with a group, always happy to share information and work through different issues and scenarios, which we haven't seen before, which aren't that many. But I think you'll find that we have solutions for the issues that are out there, and you won't be the first one that tries it. There'll be somebody else that's done it probably 20 years ago, and there's not a whole lot that we haven't come across in the past. But be happy to help out. Awesome.
We're so lucky to have you here, Stephen. And these are all the people that are on the bench, guys. You don't have to say anything, but come on and show your faces if you can. Chris Waite, branch manager with Secor. Dan Landy is an engineer with the PE Alliance, and Aaron Davey as well. So we've already had several questions roll in. And if you haven't been part of our webinar program before, that's part of the process here as we continue to talk and give you that information. We know that you're itching to have an answer to a question that is just bugging you. And they'll be able to provide that answer for you in live time, maybe get you thinking about the next question as we go through. So we're going to launch right into what we're looking at. So PPI, technical notes and technical report top 10. We'll go a little bit more than just top 10 in this, but these are are going to be some of the key technical guidance for you to be able to look at all of those pipeline problems as we come through. So some of the industry literature that is the foundation of behavior of high density polyethylene, how it works in certain municipal applications and what we should expect for its installation. It comes from the PPI's handbook on polyethylene pipe. This is a very robust book for you. It is included in the engineering package as a searchable PDF, which always helps quite a bit in it, but gives you lots of really good guidance in all those questions that might be bugging you to be able to try to process through. There's a lot more. There's pipe calculators, installation guides, technical notes and reports, case studies, fusion reports, ASTM standards, AWWA manuals, ASCE manuals of practice, and all sorts of different things. So as opposed to just give you that big fire hydrant to try to fire hose to try to drink from with all this information, we're going to try to highlight some of the best ones, tell you why they matter and what we're doing about it. So here's the general scope of the introduction of what we're presenting to you, including the documents covered. We're going to touch on specifications, design, installation, maintenance, and all sorts of other things. So Stephen Boros, you want to come on and tell us about TR3 and TR4, why their guidance is basically the foundation of how it is that high-density polyethylene meets the pressure requirements and other design requirements that we're looking at.
Yeah, I'd be very happy to. Thanks, Alan. So PPI, or Plastics Pipe Institute, has a long history of putting out technical reports and technical notes. That's really their basis and where they got started more than 50 or 60 years ago now, I believe. And so you'll see TR, which stands for Technical Report. TR3 and TR4 are one of the first publications they put out. So in order for actually any thermoplastic material, not just polyethylene, but any thermoplastic material that's used as a pressure pipe or in a pressure piping application that has to have a long-term strength determination, has to go through this process. And so TR3 is actually a very long document on all the policies and what you actually have to test in order to qualify as a certain pressure pipe grade material. Once you've gone through all that process and done all that lot of testing with hydrostatic testing, and you then get qualified and you get then published, your material gets published in TR4. So that's the real discrimination or determination between the two. TR3 is the policies. TR4 is the real listing that you need to look up and see, all right, are these materials in there? And like I said, it's all materials. It's polyethylenes, vinyls, PVDFs, polyamides, anything that's used in a pressure pipe will have a listing in this document. So it's a very valuable document to see where we are with the industry and that all of these materials you are using in your application have gone through this extremely stringent process and met all the long-term requirements to show it's going to give a very long life in a pressure piping application. So as just one example, in many materials, and let's use metallics for an example, you go off specified minimum tensile strength or SMICE to kind of classify the materials. In thermoplastics or polyethylene in particular, you can't do that. So you have to develop what's called a long-term hydrostatic strength. It's a regression curve. It's a pretty simple curve, actually. You put a number of pipes on test at different stress levels, and you see how long they take to go to failure, and you can see there's a curve. This is actually on a log-log scale, so it looks very linear. If you're not on a log-log scale and you're on just a straight table with this, Cartesian coordinates, you'll see a very extrapolate or exponential type effect. So as you get longer term out in time, but we want to know what is the long-term capability of the product, not the short term. You can do a burst and find something out, but the real long-term is what we're looking at. So that's why you have assurance that these materials have been fully tested. They have to go through a year, year and a half, sometimes 2 years of testing in order to develop this curve. And you have to do it with multiple lots of materials. It has to be analyzed. And there's a lot of different criteria that goes with it as well that gives you that confidence that a material listed in TR4 has gone through all this, has been thoroughly analyzed and studied. So an example of some of the materials you might find there. So you're going to see, let's say, for example, what is very predominant today is the material PE 4710. So if you want to see if you're, let's say, a pipe manufacturer such as ourselves or WL or whoever it might be, has their materials listing saying, I've gone and I've worked with the resin companies. I've gone and I've been analyzed by the independent listing holder. It says I can create that formulation that has gone through all of this testing. And I have shown proficiency in doing that to develop a compound that's classified as a PE 4710 and has these hydrostatic design basis ratings. So it has a rating at 73 degrees of 1600 PSI, and it has a rating at 140 degrees Fahrenheit of 1000 PSI. Now that's not pressure, remember, that's circumferential stress. So there's a formula that we use to translate stress into pressure. And so you can see that's a really good analysis. There's an online searchable tool for that as well to see who's listed in there in real time and who isn't. Another good document, there's a group called the Municipal Advisory Board, which is a semi-independent group under the Plastics Pipe Institute. And what it is a group of municipal professionals, municipal engineers, contractors, engineering design firms, and academics that have come together to say, what do we really need to look at and to specify and to get this specific information out to the municipal industry that they can very directly utilize. One of their most popular documents is what we call model specs. So MAB 3, which is the third one they published. And it's a model specification for polyethylene PE 4710, buried potable water service, distribution, and transmission pipe and fittings. So if you don't know where to start to write a specification for polyethylene pipe, this is a fantastic resource. It'll cover all the topics, all the areas that you should consider. It may or may not go into as depth as you want to go into in each one, but it's a great place to start that process so you're not starting from scratch. So I recommend anyone that is looking at your model specs, or even if you have an old model specs, we see this all the time. We have a model spec that was written in the 1990s, and it still specifies materials, it specifies test methods, it specifies standards, which aren't relevant anymore. This model spec is up to date and will bring in the new relevant resources and references that you need in your model spec. So I recommend you take a look at that as well. Some of the things you can find in there is, what type of pressure classes are there? What kind of diameter ratios are common for polyethylene pipe? Also, what is the pressure rate, not just the pressure rating of that specific polyethylene pipe for diameter ratio, for DR, but also what's its surge capability? What's its occasional surge capability? What's its recurring surge capability? This is a very unique property to polyethylene pipe, and you might as well take advantage of everything it has to offer in your design and not be strapped with some of the older ideas and thinking around surge that you have to mitigate it all the time, because polyethylene can handle it. Talks about installation. If you're doing a pull on a piece of pipe, whether it's a slip lining or even an HDD, these stresses still apply. So it's a great place to go for that kind of reference. For HDD, I think there's a reference there in 0.5 of ASTM F1962 on HDD of polyethylene pipe. It's just been updated with a lot of relevant and new information. Good resource to go to as well.
So, Stephen, one of the reasons why we look at load duration and safe pull stress, as you're well aware of, is the viscoelastic behavior of pipe allows a strain and a creep or relaxation over that time period. So actually, the apparent modulus of elasticity changes during a duration of load. That behavior is exactly what we really want for those HDD or trenchless operation installations as we go through there, because we can take advantage of some of that durability, ruggedness, and flexibility of the pipe as we go to get installed too. So those types of HDD calculations are going to be important to you if you're looking for trenchless projects as well. So definitely thank you for telling us about that. The next one I think we've got, Stephen, is to talk about anchor blocks. So anchor blocks itself, there's a key resource for you. That viscoelastic behavior that I had mentioned is also important in attenuating pressure surges in some places. So when we have water hammer coming through a pipe, essentially water hammer is a change in velocity of the flow material within the pipe. That translates directly to a change in pressure in the pipe. we look for thrust restraint along that water hammer when we have a change in direction for the pipe, or we're connecting to a valve or something of that nature. So high density polyethylene, if it was just high density polyethylene from A to B, it's called a monolithic system, which means everything from A to B is fused. And so now it's fully restrained as we see any flow movement or temperature fluctuation within that time period. The soil that surrounds that pipe is going to restrain it from moving. But when we look at anchor blocks, and here's a good resource for you, which is PPI's final report on anchor block determination, what we were really looking for is to make sure that we're not pulling that bell and spigot pipe system or the legacy pipes out of that bell and spigot. So we want to make sure that that's restrained from doing it. Everything that's fused from point A to point B will be a monolithic system as we go through, and naturally just resist that surge change as we go. This tool, and Stephen's going to talk more about it later in the HDPE app, will help you look at thrust restraint required within your system and design that thrust block for you. So I've seen thrust restraint all over the country be many different things. Engineers are conservative in nature, which is great. We are definitely adverse of failure. And then we want to make sure that we size and design these things correctly. As that translates out into the field, we also want to make sure that they don't pour the entire concrete truck right around the pipe as we go through, is that big concrete block will be something that potentially may have to be removed in the future. I'm rooted in rehabilitation. That's why I think about that such, and the fact that I've rehabilitated a lot of pipe over the years. We want to make sure that those thrust restraint designs are appropriate for the operating mode that you're expecting. And these thrust restraint to your anchor blocks will definitely take a look at that for you. AWWA's M55 manual is rather robust in what it's able to provide you with interesting, good new information. Well, it's a redefined from the first generation, of course, but definitely all of the equations that you need to be able to operate or install this pipeline as we go through to look at the different applications that you may enter into. Yes, Richard, please. You're on mute, Rich.
Jeremy asked a question regarding ASTM F1962, and Stephen, since you're at ASTM, he asked, is the latest edition 2020, or is it 2223? Can you verify that at all, or I don't have quick access to that?
Let me take a look at it and see. It was just published, I think, last year, so it's going to be a 2022 version, but I will double check on that while we're here.
Thank you very much.
Richard, thank you for bringing that up. So just to let you know, guys, Stephen's calling into our meeting from the ASTM standards meeting as we go through there. So yes, you are directly connected with those people that are going to have that information for you. So the Alliance's engineering package, we mentioned it previously. This is a key resource for you that's free and available to you. All you have to do is ping Mr. Landy through this, and then he'll be able to provide you with that engineering package. We are going to get a 2023 update this year. It's in the works. It's in the books. We're looking at publishing sometime in the third or the fourth quarter through that. That'll have an expanded set of specifications, additional typical details as we go through there, and then additional information as these technical notes continue to be released and provide you with great resources through that process. So definitely look out for that engineering package as we go through. And here we're going to roll right into the material handling guide. Stephen, if you want to come on and take a look and tell us about what we're looking at here. PPI has produced some field manuals as to how to properly handle HDPE as we go through.
Yeah, thank you. So just to follow up on Richard really quick, F1962 does have a 2022 version. So it's -2022 is the latest. And Dr. Larry Slavin kind of took that on as far as leading that task group. So if you want to get that updated one, it's available on ASTM. PPI Material Handling Guide. This is a fantastic guide because polyethylene, because it comes in 50-foot joints or 40-foot joints, typically, normally 50, has a little bit different handling than you might have used for other materials. So just to understand how to handle it, how to load it, how to ship it, how to unload it when it gets to the job site is extremely important. Not just to protect the pipe, but also for safety considerations as well. There's just some things that you need to make sure, as you do on any job site, in order to work safe. But the material handling guide that PPI puts out really gives you a good understanding about what I need to look for and how I need to move polyethylene around. This is a great example. So here's some, I believe it's 63-inch pipe. Of course, it's not, you'd like to pick it up with straps. You could pick it up with a forklift from the bottom, but then could it roll off? Could it do other things? So moving polyethylene around with straps is always the preferred methodology. If it's in a single piece, for sure. If it's bundled in a package, then you could pick it up from the bottom with forks. But again, you need certain depth and things like that. When you get to the job site, you need to make sure you're capable of unloading the pipe in the right way. We see a very skilled front-end loader driver here who's measuring how he's going to get this pipe very safely off the truck and onto the job site. The truck driver is actually videoing this because he's staying well away from the action, as he should on a job site. And once you see how he's going to line this up, make sure he moves the pipe very carefully. There he goes and moves the top layer right off the truck. That's an example of what you don't want to do. Many people do it. I know polyethylene is an extremely tough and durable product. You can do it, but it certainly is not the preferred way for a lot of reasons. The other part of that from a safety aspect is if there was someone standing on the other side of that the loader could not see, that could be very detrimental from a safety standpoint. So again, an example of what not to do. Incoming material checking at the job site is another very important aspect of material management. So this is a sheet that's within the material handling guide. I recommend everybody take a look at it and utilize it. So it kind of runs through what do you need to look at when a load of truck arrives on your job site? What's the project name, where it's coming from, who's the pipe supplier, what standard is the pipe supposed to be made to? And what does it say on the print line? Is it NSF certified? What type of material is it? What's the diameter? And what's the diameter ratio of the pipe? Just to make sure everything got there and it's the way it's supposed to be. If you want to do on-site damage inspection, you should do that at the time as well. Remember, polyethylene does have a 10% allowable scratch depth. So while no pipe should arrive on a job site with scratches and gouges, if it does from handling in the field, a 10% allowance means you don't have to do anything with it. You can simply go on once you measure that 10% of the wall thickness of the pipe. But again, you can check all this and make sure you the materials arrived on site, they've been inspected, and they are what they believe they are. The last thing you want to do is when the fusion operator goes to pick up that piece of pipe to fuse it, he finds out it's a different OD than what he had yesterday. That's probably not a good idea.
Okay, so we are looking at butt fusion here, technical note 51. Thank you very much for that, Stephen. Rusty, come on and tell us what we're looking at here. So the butt fusion process itself is controlling the flow of molecules across the pipe interface in the field with appropriate heat and appropriate virgin resin. And by doing so, we get a joint that is as strong, if not stronger, than the pipe itself. Right, Rusty?
Exactly. And really with all the, polyethylene has just some incredible characteristics and properties, but really I think the heat fusion joint is probably one of the most critical for, water and wastewater applications. It basically is giving you a zero leak rate. You have no other materials in there. You don't have rubber gaskets that are going to fail, 10, 20 years down the road. And it's one of the reasons why we can provide a 100-year service on a properly installed, properly specified polyethylene piping system. So basically with the fusion, you square the pipe ends. You have a machine that generally from McElroy, mostly in the US. There are some other manufacturers out there. McElroy is definitely a great manufacturer for us. You line the two ends of the pipe. You have the pipe to where they're fairly level, bring them together, and then you're going to face that. That's what you're seeing right now is the facer. And it's basically taking those two ends of pipe and squaring them up, as well as eliminating any oxidation, any scratches, any material that would be on the ends of that pipe. Once that facing is done, you drop your heater in, and at that point, you have some pressure where you're pushing the pipe ends against the heater to kind of get a melt bead going, your melt swell. And after that, you pull the heater out and you push those two ends of pipe together. And that is where you get your rollback bead, as you're seeing here, that rollback. Now, it's very, very important to know the bead, one, does not really affect flow. I know some people want to go in there and take that bead out. The C factor of 155 for polyethylene includes that bead and is not a problem. The joining method is in that wall thickness. You can see with the colored one there, that's not just a candy colored pipe there. We did that to kind of show how those melt flows go. So you'll see how the interface of the two pipe coming together under a high temperature that has allowed those links to open up. Then putting it under pressure, you have that joining of that, and then you see the excess pushing out to the edges. Again, that excess doesn't have anything to do with any of the pressure rating or anything like that. It's fine whether the exterior or the interior is removed. This is a cross section, I'm sure you realize, but that those multicolors show how that becomes one monolithic pipeline, and that can be for a mile or 100 miles. If you're fusing that pipe, you've got one material in there, and that fusion joint is just as strong as your pipe. When the pipe is tested, a fusion joint is tested, you're looking for the pipe to fail prior to the fusion joint. And you generally see that well above two to 4 times the pressure rating. It's usually in the 4 to 5 range, to be honest with you. So yeah,
Absolutely.
The fusion is definitely one of the key components of polyethylene, and it's one reason too why it is used in so many no-dig applications. It's very difficult to be using a jointed pipe or a very stiff pipe in a no-dig application, whether it be pipe bursting or anything like that. So this monolithic pipe is what allows you to use those in no-dig, pipe bursting, and HDD and that type of thing. Did you have something to say there, Alan? I'm sorry.
My apologies. Yep, just we're controlling the flow of the molecules at the molecular level across this interface, whether or not we do it through extrusion, which has more controls through the process, but we're still doing the same basic structure, which is allowing that virgin resin material, which is really hydrogen carbons with a little bit of additives, to flow across that interface and then give us the combined strength of semi-crystalline and amorphous regions that we're really looking for. So this TN51 will really show us that. And next we've got MAB0102. Rusty, go ahead and tell us about the electrofusion procedures. This is the similar process. Now we just use an embedded copper coil to generate that heat through that.
Exactly. And really both of these, the MAB01 and 02, as well as TN51, are fairly recent and the ASTM standards for the fusion. And it's very key because, like I said, this is a key component of polyethylene. But yes, so for the electrofusion, you have a little bit more prep. I consider butt fusion the number one. Electrofusion for connecting polyethylene would definitely be number 2 methodology. And you basically have to, you're prepping that pipe very similar to the butt fusion, except you're scraping instead of facing the ends of the pipe. You get a square cut end. You are going to prep the outside of that pipe to make sure you don't have oxidation or any excess materials. You'll clean it with an approved cleaner to make sure everything is cleaned off. And then you're going to have markings on those electrofusion couplers or fittings. Another very key component of electrofusion would be adding like a saddle for services and that type of thing. Very useful for the polyethylene for a water system or sewer system. And basically you do have to have some control. And I'll reinforce both for butt fusion and for electrofusion, you want to make sure that you have got a well-qualified and trained technician. That should be something that should be in your specification. And speaking of that, I think all of our sample specs would go into that as far as covering this, making sure you have a good qualified and trained technician that's doing that work for you. Actually, the cleaner used would be a 90% isopropyl alcohol. And again, once that is cleaned up, you'll have measurement to get the coupler in the right place, and then you'll hook that up to a box, and it will give you a no or a no-go. So that box will tell you whether you've got a good coupling fusion on that particular joint, and will allow you to track that as well. The other thing I would mention on electrofusion, again, you've got L's, T's, reducing T's, service saddles. You can do hot taps on this as well. So the electrofusion does provide you a lot of flexibility. The one thing I would mention, again, MA, we're kind of touching the surface here, but both TechNote 51 as well as MAB 01 and 02 will go into much more detail, much more explanation, but these would be key for kind of determining how you want to join that pipe.
So it sounds like there's just a few more steps as we go through in an operator process than in the butt fusion process, than for electrofusion itself. But in small diameter, those service connections actually are much easier to fit into those areas as opposed to a full butt fusion machine.
Correct.
So that's a true benefit of it as well.
For repairs or in ditch connections, the electrofusion can be, really good. You use a lot smaller machine. It's much easier to do, though there are in ditch butt fusion machines as well. So
absolutely. So
yeah.
Thank you very much, Rusty. Within the overall HDPE industry, we don't make larger diameter valves. So those are all going to be metallic. And Stephen, come on and tell us a little bit about how we would connect to those metallic valves. There's definitely some conservative fittings that have been designed that are rather robust to be able to make sure we connect to those valves and other appurtenances that have to be within that system itself. So
absolutely.
Yes.
So yeah, you're going to have to connect a flange to something at some point in time on a system. So on polyethylene, we use what's called a flange adapter. So it's a machined usually or molded piece that creates the flange. That is typically butt fused to the end of the polyethylene pipe using the typical butt fusion process. And then it can get flanged up with a backing ring and bolts, just like any flange, to an appurtenance, such as a valve or whatever else you may have that you need to connect to. So the only thing about polyethylene is you just need to make sure that it's torqued properly because it does creep slightly. Getting the right torque force is very critical to making sure you get a very tight seal and a leak-free seal. One nice thing about polyethylene and the flanges is that if you're connecting, as you see here in the picture, a polyethylene to polyethylene flange adapter or flange, you don't typically need a gasket. The polyethylene has the right durometer to go ahead and seal without using a gasket to put in there at all. If you do need a gasket or just want to use a gasket, make sure you match proper durometers to match the type of force that you're going to be applying to it, as you see here. So the torquing pattern and the amount of torque that you put on each bolt is how you go about getting that right process. The last part of this is to make sure you come back after 4 to 24 hours and do a final torque after it's all settled in, after it's moved and done a little bit of creep, to make sure that those bolts haven't loosened at all and you still have the same amount of force in each one. But a very valuable tool for installing any system. If you are doing butt fusions, a good way to monitor that and make sure that it's all done properly is to use what's called a data logger. There is a ASTM standard practice for what a data logger should do. ASTM F3124 gives you kind of the standard procedure of how you go about using a data logger and the types of measurements and things that it should do and record to make sure that you have a good butt fusion. The process of a butt fusion is very simple. You have several steps. After you face it and clean it, as we saw earlier, and you have the square things, you're going to put the heater plate in, and you're going to do an initial beat up is what's called, to make sure all the surfaces are contacting that heater plate. Then once you have that initial beat up, which is very small, you release all the interfacial pressure, so it's just touching that heater plate. Then you get a heat soak. That's going to make sure you develop the right melt profile into the wall of the pipe to give you that jointable surface. Once you have that, you're going to then remove the heater plate, as you should see there, and then you're going to bring the pipe ends together in a very controlled way at a prescribed interfacial pressure. Now, the hydraulic fusion machines will do that automatically for you once you do the calculation. Once you bring it together and hold it, then you're just waiting for it to cool. It's very simple. But you have to hold that interfacial pressure while it's cooling. The data logger will record all of these values and times to make sure all the processes were followed. Once you follow the process, your chances of having a good joint are probably 99.9%. Just from looking at this curve on a data logger, you can say, I'm confident that's going to be a good joint. Richard.
Yeah, just to add to this, cooling time is really critical because of rough handling, because remember, you're going from a molten to a solid state. And the reason that interface is kind of hourglass in shape is because the inner surface is hottest. So you get more flow for longer periods of time in that system. The heat soak under no pressure is really also important, so you don't push that molten or flowable material away from those two end surfaces. So it's really, really critical. Another thing to consider, and the reason this graph is so important, is the open time that plate is. Well, what if you're minus 10 degrees or you're plus 80 degrees? It's really, really critical that we understand these curves and then have these for your records. And usually how they're identified is the technician will label them as he goes along. So it really gives you that assurances. But if we see something different in this type of cycle to review, then you might want to question that that particular fusion. And if it looks a little bit questionable, then you can cut it out and redo it.
We just had a great question from Steve Jackson here. What is cooling time? How long is that? That's DR dependent and then also size dependent. One of the cool things about the data logger is it's so easy to use once it has been associated with the butt fusion machine that the operator that's performing those butt fusions is just like second nature to them as it goes through there. So that's a great topic. We got to keep moving. We got a little bit to cover here. One of the most things that's unique about polyethylene is our ability to be able to squeeze that pipeline off. This comes from the natural gas market quite a bit, and the fact that they can temporarily squeeze that pipeline off to shut the flow of gas through any line to be able to perform whatever repair they've got going, and then move on quickly. That hasn't been adopted as much in the municipal water application. We get larger pipe sizes as we go through there, but technical note 54 will be able to show you through it. Of course, the presence of water during our fusion process is not going to be good for our overall process. But there are time periods defined based on the DR rating and the size of the pipe to go down and then come back up. You can go faster. Let's say it's 2 a.m. in the morning and you've got a pipeline that you have to shut off. You can go faster, but you'll just put a repair clamp around that pipe in that specific location as we go through. So here's a good guide for the time period as to which we occlude the pipeline, and then the time period as to which we come back to open up that orifice. And we're looking really for avoiding yield of the actual material itself through there. Here's another good guidance for us, MAB 04 repair options. This has developed and grown fairly significantly over the past 10 years. The MAB has been very influential in be able to make sure we have those options. In reality, a lot of the reasons why people 10 years ago would not adopt high-density polyethylene is because they thought, oh, how am I going to repair it? Well, I'll just cut to the brass tacks. Most of the fittings that you work with on a routine basis, that you'd go out in the middle of the night or just after the Super Bowl, as that's a high demand time period, to be able to repair your water main at that time period, can use similar fittings. It is not going to be a fusion fitting unless you specifically go out there with fusion tools, but you can come back at a later date to be able to do that fusion as we go through. So the MAB 04 shows you a decision matrix as to what type of repair is required, what type of damage to the pipe is required, and then it shows you exactly what type of fitting can be able to be used to perform that repair as we go through. So if it's a small leak, what do I use? We get larger into all the different steps. It'll really walk you through all those steps as we really need to see it. So in summary, there's lots of good resources for you. We've attempted to show quite a bit of those resources as we move forward, but now we want to really pivot and show what does this look like in the field? What does it look like with case studies? How are we going to work through calculators and tools? And we have a good list here of case studies, as we said, on the pepipe.org website for you. And Rusty, if you want to come on, we've got a little bit to talk about here with large diameter pipe. As an industry on whole, we've been noticing that there's significant concern over evaporation or evapotranspiration by losing water within an open canal. And there's been efforts to be able to push through high density polyethylene in a large diameter. So let's try to be as succinct as we can. Rusty, I see you're the star of the show in some of these pictures out on site. So that's great to be able to see. Tell us what's going on.
Yeah, this is a great project. And I think the key thing on this too, of course, people are wanting to know how to pay for these projects. And a lot of this is funded. I mean, the government will contribute to helping enclose some of these canals to allow you to have more water. On this particular project, you can see the quantities up there, very large diameter, a lot of footage. And their anticipated savings from this when they first designed the project was 25%. After they got going on it, they determined with leakage as well as the evaporation, they really anticipate 40% savings in their water. They're going to have that much more water. So just especially in these times with the droughts and the weather conditions that we're having, just a really great project that is helping the agricultural industry. This project
Sure.
was out in Utah.
Across the board, municipalities are about a 15% water loss throughout in the potable water system. So looking towards a leak-free joint is really going to help us, especially in these arid regions. So here's a force main project, Rusty. I like this one because the contractor's taking advantage of that long lay length, and they're opening up a big excavation to maximize the productivity. So what are we looking at here, Rusty?
And exactly. And again, as anybody who's been to California, things are tight out there. They don't want you closing roads or highways. They were able to keep this highway at least partially open while they installed this project. You've got duality on the piping. If you have a problem, granted, it would probably cut down on some of the capacity that you have, but you do have, two different lines running there. And as congested as California is out there, this was just a great project. The interesting thing on that, you see those two pipes and how close they are together. That's where some of this in-ditch fusion or possibly electrofusion can come in there and help you do a really tight connection in the ditch where you had to. But most of these lines were done above ground and then put in place. So just an excellent project for force main replacement.
Love it. That's one of my main questions is redundancy, Rusty, especially when we're looking at rehabilitating larger pipes. So I'm so glad that you mentioned that there's redundancy in both of these lines.
Exactly.
So, Stephen, you want to come over and talk about some of the technical software we have available? There's multiple apps for you. They, of course, are online, free of charge, and they're pretty easy to get through. HDPE app, Stephen's going to talk about, and I'll talk right through Boraid right after that, and we'll keep going. Okay, here we go.
Absolutely. So HDPE app's probably one of my favorite online design calculators for polyethylene pipe. It goes through all the aspects of it. So just type into your browser www.hdpeapp.com, and it pretty much operates like an app on your phone, but it's not a downloadable icon. But it is mobile friendly as well. So if you have a tablet or you got to use it on your phone, you can do that. So once you go in and accept the liability issues and all of that, then it kind of gives you a screen here, and you pick what type of material you're using, the sizing system, IPS or DIPS, the OD of the pipe and the DR of the pipe, and automatically gives you a lot of properties of the pipe right there. There's a lot of valuable information just here alone. If you look at the bottom of the screen where it says fixed and calculated values, where it says more, as you click on that, it'll give you a list of another dozen or so properties of the polyethylene pipe. It'll give you the minimum wall, temperature correction factor, hydrostatic strength. What's my inside diameter? 5,000 feet of pipe. What's my internal volume of this size pipe? So if I need a pressure test, I know how much water I need to bring on site to pressure test it with. It'll give you the maximum pressure rating at 73 degrees, or if you want to use it at a different temperature, it'll give you automatic temperature derating factor if you want to use it at 100 degrees per se, what the temperature changes to be. So just from that application alone, there's a lot of good information to get from. If you want to do a pressure piping design, it'll run through all of those scenarios for you as well. It'll give you the frictional pressure drop. It'll give you the max flow capability. It can calculate, depending on what variable you want to solve for, it'll show you that as well. So I'll remove these a little quick. So for instance, let's say this is a great example. So you're moving at a frictional pressure loss of, let's see, you have a mile of pipe and you want 750 gallons per minute. I'm going to have 37 PSI pressure drop through that mile of pipe. My fluid velocity is going to be 6.3 feet per second. And my resulting surge capability, if you have an immediate drop or water hammer event, is only going to be 91 PSI. So you can see right then, is this pipe capable of handling that, or should I upsize it, or can I downsize it? 6.5 feet for polyethylene pipe is a very acceptable design flow rate because of its enhanced surge capability.
Absolutely, Stephen. So that brings us back to that viscoelastic behavior we talked about and the surge resistance that the pipe has. So again, on top of the design capacity, we have 1.5 times that PSI for recurring, 2 times for occasional. So there's still a lot of headroom right above it. So here we talk about some installation questions we've got. We did get a question pre-show about above ground installation. And here, definitely walk through these slides for us, Stephen.
Sure. So you see this a lot as well. Well, polyethylene has a really high thermal expansion coefficient. So, how am I going to control that? It does have a higher expansion coefficient than some other materials. You can see here for a given length of pipe, for a given temperature differential, that length of polyethylene pipe could grow as much as 8 inches, wherein if you're looking at steel pipe, it's less than an inch, less than 1/2 inch. So you're saying, wow, that's huge. How am I going to ever mitigate that? The nice part about it is because the elastic modulus on polyethylene is lower compared to steel pipe, it's a lot easier to constrain that stress or that potential growth or contraction of the pipe because the force generated is so much less. So you can see that it's only 321 pounds to constrain that versus 8,000 pounds to constrain the same amount, or same size of steel pipe for the same condition. So again, it's very easy to mitigate any of those concerns. The rule of thumb on polyethylene pipe, this is a great one to kind of throw out there, is 100 feet of pipe with a 10-degree differential will change 1 inch. So you get the 100-10-1 rule when you're looking at something like that. So again, for every 100 feet of pipe, 10-degree temperature change, you're going to change a potential length of 1 inch. I talked earlier about the mitigation options. As you see here, the expansion of the pipe isn't always a concern or an issue. Maybe you have enough right away to take care of that. If you don't, you want to say, all right, I want the pipe to stay within these bounds. There's ways to control that very easily. Lateral deflections can be controlled for expansion loops. You can have guided anchored systems all along the pipeline system to make sure that it stays within the 2 anchored points, or you can have a conventional expansion loop. Polyethylene is very well suited for all of those types of mitigation situations.
Definitely. So we've got a few other things to talk about here, below ground equations as we go back to the HDPE app. Just a reminder, if you wanted those PDHs to complete the survey at the end, that's the easiest way to get through to it. We won't be able to make it through all the material today, unfortunately, but there's a lot of information, and you can definitely reach out to us afterwards. So keep going, Steve.
Okay, sorry. You know, if you want to look at, I'm not going to go through all the examples just because we're running a little bit short of time. But if you want to know what your external pressure ratings are, buckling forces, soil forces, how it affects ovality and things like that of the pipe, HDPE app will take care of that for you. Let's go ahead and move to the next one, Alan.
Yep. If you had some theoretical calculations to go through, they'll show you the deflection. That's the primary one in open cut construction that we have to really look at. A lot of this comes from AWWA's calculations and PPIs. Now, for most of us on the call, 95% of your installations are simply going to be within this design window of a DR7 to a DR21, minimum depth of cover, H20 loading. That's a box truck with 3 feet. Without the H20 loading, that's a 2 feet, and then now a maximum depth of cover for 25 feet. So if you had to continue to do your design analysis, you didn't fit within that time period, the Alliance does have calculators for you to be able to run through all those connections and calculations as we see fit. It's a combination of soil loading, live loading, and surcharge on top, and then a pipe stiffness factor and a soil stiffness factor to underneath that denominator to be able to come through and calculate those for us. So we want to keep going through to Boraid. Boraid's a wonderful tool for you. We only have a few more minutes here. Essentially, this will walk us through pipe design for a horizontal directional drill and a bore path. You'll enter in the values as to what size pipe, DR rating of the pipe. Look at your bore design as we go through the depths of it, where we're going to try to traverse that obstruction, the lengths of each curves or section of each curves as we go through. And then it'll pop out these results for us to see whether or not our loading duration during that live loading period was too much for that DR rating on the pipe as we went through. Again, this is all available to you. It's still a planning tool. As competent civil engineers out there, you need to do your own calculations to back up your analysis and design. So, Steve, we've got about 2 minutes left to be able to look at PPI PACE, which is a perfect ending, and go ahead and let us know what we're looking at.
Perfect. PPI PACE, pipe analysis and calculation environment. So this is designed to take all the AWWA design manuals for ductile iron, polyethylene, and PVC pipe and do a direct comparison on your operating conditions. So let's say you want pick a certain size pipe, let's say 10-inch dip size pipe, and you pick your diameter ratio of the pipe that you want to compare. And then you're going to put in typical operating conditions, say 1,000 feet of pipe. You could pick whatever you want. What's my design recurring surge? What's my design velocity for occasional surge? What's my average working pressure, anticipated surges per day, my average annual operating temperature, not your instant one, but the average. And then what is the minimum design life I'm looking for on this system? You should never pick anything less than 100 years for that number. It's going to go through and tell you where all these values have come from, you know, why you're using these certain values for your design. And then it's going to go through and do a direct calculation from each one. Next slide, Alan. So once you go in and pick all these, if you click on the radial dot there where you see where the aerial is, it'll go back and tell you where these values come from and why you should be using certain values in that region, just to give you a little additional background. So in the results section, it's going to tell you, all right, if I'm using this size pipe, did I pick the right diameter and DR for these type systems that will give me a true 100-year design life? And you can see in which situations, again, comparing apples to apples directly with that system, which ones work and which ones don't. It's a great tool to go in and pick different scenarios. You can look at what your flow rates are, your surge capacities are. Remember, because for the same situation, all these different materials, these pipes will give you a different surge value, and they're going to have different capabilities and different resulting surge for the same instantaneous flow velocity changes. So anyway, great first tool to go through. Be happy to work through it with anybody else who needs it.
Awesome, Stephen. Thank you very much for your patience running through that last bit of it. Rusty, come on. Richard, also as well. We're right at the very end of this. We've had a couple of more questions. We've had over 30 questions as part of this. So thank you guys very much for your participation. Your participation always makes these better because we get to directly answer those questions that we've got. Here's contact information for everybody on it. Again, if you want PDHs, the survey will come up at the close of the webinar itself. If you want the engineering package, just make sure you email dlandy@pepipe.org for that engineering package. Our webinar out. We do a lot of webinars. We do a whole lot of webinars. And guess what? A lot of them are available on our YouTube channel. So if you're working away there and you got that burning question as well, what did they say? What did Rusty say? What did Stephen say in this one instance? You can go look at our YouTube channel and be able to help do that. So it's we run a full program outside of just ASCE. We're very happy and pleased that ASCE is how you found this webinar. Sometimes you don't always find everybody that you're looking for, but we found you and you found us today. And anybody had any extra comments at the end of this, Rusty or Richard?
Yeah, I had one quick comment. I'd just like to point out about PPI or the PACE that we just talked about. You know, that because it's comparing different materials and maybe competitive materials. I think many people probably think the polyethylene industry did that. It was actually a third party that actually did that. It had nothing to do with the industry. I believe it was a college that actually designed that program. So I think that's just a key point. It gives it a lot of credibility that way.
Yeah, and great questions today, everyone. I know we try to spank them off as much as we can, but there's a lot of detail behind, especially on the velocity questions. That's where the PACE will help you. Just thanks to the PE Alliance, for putting these together. We really appreciate it because we get to send the stories to you guys. And even though my friend here, Stephen, is my direct competitor, we work a lot together to make sure things are done properly, because if they're done properly, like any good design system, they should last a long, long time. And hopefully we'll see the end of some of the, extend the lifetime of what we're offering as a piping product. So great job, guys. And I really appreciate being here, ASCE, and hopefully you'll have us back.
Yep.
Absolutely. And thank you to all the speakers for sharing your HDPE knowledge, and for the Alliance for PE Pipe, along with W&L Plastics and Core and Maine for sponsoring this valuable presentation. We look forward to your next webinar in September. I put the link in the chat for everyone to register, so you don't want to miss that. And a huge, tremendous thank you to all the attendees that joined us today. We hope everyone stays well and has a great rest of your day.
Thanks,
Goodbye.
everybody. Appreciate it.